QLoRA, efficient fine-tuning of quantized LLMs. Abstract. We present QLoRA, an efficient fine-tuning approach that reduces memory usage enough to fine-tune a 65B parameter model on a single 48GB GPU while preserving full 16-bit fine-tuning task performance. QLoRA backpropagates gradients through a frozen, 4-bit quantized pre-trained language model into low-rank adapters, LoRA. Our best model family, which we name Guanaco, outperforms all previous openly released models on the Vicuna benchmark, reaching 99.3% of the performance level of ChatGPT while only requiring 24 hours of fine-tuning on a single GPU. QLoRA introduces a number of innovations to save memory without sacrificing performance: a 4-bit NormalFloat, NF4, a new data type that is information theoretically optimal for normally distributed weights, b. double quantization to reduce the average memory footprint by quantizing the quantization constants, and c. paged optimizers to manage memory spikes. We use QLoRA to fine-tune more than 1,000 models, providing a detailed analysis of instruction following and chatbot performance across 8 instruction datasets, multiple model types, LLaMA, T5, and model scales that would be infeasible to run with regular fine-tuning, for example 33B and 65B parameter models. Our results show that QLoRA fine-tuning on a small high-quality dataset leads to state-of-the-art results, even when using smaller models than the previous SoTA. We provide a detailed analysis of chatbot performance based on both human and GPT-4 evaluations, showing that GPT-4 evaluations are a cheap and reasonable alternative to human evaluation. Furthermore, we find that current chatbot benchmarks are not trustworthy to accurately evaluate the performance levels of chatbots. A lemon-picked analysis demonstrates where Guanaco fails compared to ChatGPT. We release all of our models and code, including CUDA kernels for 4-bit training. 1. Introduction. Fine-tuning large language models, LLMs, is a highly effective way to improve their performance, and to add desirable or remove undesirable behaviors. However, fine-tuning very large models is prohibitively expensive. Regular 16-bit fine-tuning of a LLaMA 65B parameter model requires more than 780 GB of GPU memory. While recent quantization methods can reduce the memory footprint of LLMs, such techniques only work for inference and break down during training. We demonstrate for the first time that it is possible to fine-tune a quantized 4-bit model without any performance degradation. Our method, QLoRA, uses a novel high-precision technique to quantize a pre-trained model to 4-bit. Then adds a small set of learnable low-rank adapter weights that are tuned by backpropagating gradients through the quantized weights. QLoRA reduces the average memory requirements of fine-tuning a 65B parameter model from greater than 780 GB of GPU memory to less than 48 GB without degrading the runtime or predictive performance compared to a 16-bit fully fine-tuned baseline. This marks a significant shift in accessibility of LLM fine-tuning. Now the largest publicly available models to date fine-tunable on a single GPU. Using QLoRA, we train the Guanaco family of models, with the second-best model reaching 97.8% of the performance level of ChatGPT on the Vicuna benchmark, while being trainable in less than 12 hours on a single consumer GPU. Using a single professional GPU over 24 hours, we achieve 99.3% with our largest model, essentially closing the gap to ChatGPT on the Vicuna benchmark. When deployed, our smallest Guanaco model, 7B parameters, requires just 5 GB of memory and outperforms a 26 GB alpaca model by more than 20 percentage points on the Vicuna benchmark. Table, TBL Vicuna_eval. QLoRA introduces multiple innovations designed to reduce memory use without sacrificing performance. 1 4-bit NormalFloat, an information theoretically optimal quantization data type for normally distributed data that yields better empirical results than 4-bit integers and 4-bit floats. 2. Double quantization, a method that quantizes the quantization constants, saving an average of about 0.37 bits per parameter, approximately 3 GB for a 65B model. 3. Paged optimizers, using NVIDIA Unified Memory to avoid the gradient checkpointing memory spikes that occur when processing a mini-batch with a long sequence length. We combine these contributions into a better-tuned LoRA approach that includes adapters at every network layer and thereby avoids almost all of the accuracy trade-offs seen in prior work. QLoRA's efficiency enables us to perform an in-depth study of instruction fine-tuning and chatbot performance on model scales that would be impossible using regular fine-tuning due to memory overhead. Therefore, we train more than 1,000 models across several instruction tuning datasets, model architectures, and sizes between 80M to 65B parameters. In addition to showing that QLoRA recovers 16-bit performance, Section 4, and training a state-of-the-art chatbot, Guanaco, Section 5, we also analyze trends in the trained models. First, we find that data quality is far more important than dataset size. For example, a 9K sample dataset, OAST1, outperformed a 450K sample dataset, FLAN-B2, subsampled, on chatbot performance, even when both are meant to support instruction following generalization. Second, we show that strong massive multitask language understanding, MMLU, benchmark performance does not imply strong Vicuna chatbot benchmark performance and vice versa. In other words, dataset suitability matters more than size for a given task. Furthermore, we also provide an extensive analysis of chatbot performance that uses both human raters and GPT-4 for evaluation. We use tournament-style benchmarking where models compete against each other in matches to produce the best response for a given prompt. The winner of the match is judged by either GPT-4 or human annotators. The tournament results are aggregated into LO scores which determine the ranking of chatbot performance. We find that GPT-4 and human evaluations largely agree on the rank of model performance in the tournaments, but we also find there are instances of strong disagreement. As such, we highlight that model-based evaluation, while providing a cheap alternative to human annotation, also has its uncertainties. We augment our chatbot benchmark results with a qualitative analysis of Guanaco models. Our analysis highlights success and failure cases that were not captured by the quantitative benchmarks. We release all model generations with human and GPT-4 annotations to facilitate further study. We open source our codebase and CUDA kernels and integrate our methods into the Hugging Face Transformers stack, making them easily accessible to all. We release a collection of adapters for 7/13/33/65B size models, trained on 8 different instruction following datasets, for a total of 32 different open-sourced, fine-tuned models. Background: Blockwise k-bit quantization. Quantization is the process of discretizing an input from a representation that holds more information to a representation with less information. It often means taking a data type with more bits and converting it to fewer bits, for example from 32-bit floats to 8-bit integers. To ensure that the entire range of the low-bit data type is used, the input data type is commonly rescaled into the target data type range through normalization by the absolute maximum of the input elements, which are usually structured as a tensor. For example, quantizing a 32-bit floating point, FP32, tensor into a int8 tensor with range -127 to +127, x int8 is equal to the result of rounding the product of x FP32 and 127 divided by the absolute maximum of x FP32, all multiplied by x FP32. It is also equal to the result of rounding the product of c FP32 and x FP32. Where c is the quantization constant or quantization scale. Dequantization is the inverse. Dequantization of c to the power of fp32 and x to the power of int8 is equal to x to the power of int8 divided by c to the power of fp32, which equals x to the power of fp32. The problem with this approach is that if a large magnitude value, i.e., an outlier, occurs in the input tensor, then the quantization bins, certain bit combinations, are not utilized well with few or no numbers quantized in some bins. To prevent the outlier issue, a common approach is to chunk the input tensor into blocks that are independently quantized, each with their own quantization constant c. This can be formalized as follows: we chunk the input tensor x as a matrix in real numbers of size b by h into n contiguous blocks of size b by flattening the input tensor and slicing the linear segment into n equals the product of b and h, divided by b blocks. We quantize these blocks independently with equation 1 to create a quantized tensor and n quantization constants c sub I. Low-rank adapters. Low-rank adapter, LoRA, fine-tuning is a method that reduces memory requirements by using a small set of trainable parameters, often termed adapters, while not updating the full model parameters which remain fixed. Gradients during stochastic gradient descent are passed through the fixed pre-trained model weights to the adapter, which is updated to optimize the loss function. LoRA augments a linear projection through an additional factorized projection. Given a projection x times w equals y with x is an element of the set of real numbers with dimension b by h, w belongs to the set of real numbers h by LoRA computes, y is equal to x times w plus s times x times L sub 1 times L sub 2. Where bold L sub 1 belongs to real h by r and L2 in r to the power of r times o, and s is a scalar. Memory requirement of parameter-efficient fine-tuning. One important point of discussion is the memory requirement of LoRA during training, both in terms of the number and size of adapters used. Since the memory footprint of LoRA is so minimal, we can use more adapters to improve performance without significantly increasing the total memory used. While LoRA was designed as a parameter-efficient fine-tuning (PEFT) method, most of the memory footprint for LLM fine-tuning comes from activation gradients and not from the learned LoRA parameters. For a 7B LLaMA model trained on FLAN v2 with a batch size of 1, with LoRA weights equivalent to commonly used 0.2% of the original model weights, the LoRA input gradients have a memory footprint of 567 MB while the LoRA parameters take up only 26 MB. With gradient checkpointing, the input gradients reduce to an average of 18 MB per sequence, making them more memory intensive than all LoRA weights combined. In comparison, the 4-bit base model consumes 5048 MB of memory. This highlights that gradient checkpointing is important, but also that aggressively reducing the amount of LoRA parameter yields only minor memory benefits. This means we can use more adapters without significantly increasing the overall training memory footprint. See Appendix 16 for a detailed breakdown. As discussed later, this is crucial for recovering full 16-bit precision performance. QLoRA fine-tuning. QLoRA achieves high-fidelity 4-bit fine-tuning via two techniques we propose: 4-bit NormalFloat, NF4, quantization and double quantization. Additionally, we introduce paged optimizers to prevent memory spikes during gradient checkpointing from causing out-of-memory errors that have traditionally made fine-tuning on a single machine difficult for large models. QLoRA has one low-precision storage data type, in our case usually 4-bit, and one computation data type that is usually float 16. In practice, this means whenever a QLoRA weight tensor is used, we dequantize the tensor to float 16, and then perform a matrix multiplication in 16-bit. We now discuss the components of QLoRA followed by a formal definition of QLoRA. 4-bit NormalFloat quantization. The NormalFloat, NF, data type builds on quantile quantization, which is an information theoretically optimal data type that ensures each quantization bin has an equal number of values assigned from the input tensor. Quantile quantization works by estimating the quantile of the input tensor through the empirical cumulative distribution function. The main limitation of quantile quantization is that the process of quantile estimation is expensive. Therefore, fast quantile approximation algorithms, such as SRAM quantiles, are used to estimate them. Due to the approximate nature of these quantile estimation algorithms, the data type has large quantization errors for outliers, which are often the most important values. Expensive quantile estimates and approximation errors can be avoided when input tensors come from a distribution fixed up to a quantization constant. In such cases, input tensors have the same quantiles, making exact quantile estimation computationally feasible. Since pre-trained neural network weights usually have a zero-centered normal distribution with standard deviation sigma, see Appendix 15, we can transform all weights to a single fixed distribution by scaling sigma such that the distribution fits exactly into the range of our data type. For our data type, we set the arbitrary range left bracket -1, 1 right bracket. As such, both the quantiles for the data type and the neural network weights need to be normalized into this range. The information theoretically optimal data type for zero mean normal distributions with arbitrary standard deviations sigma in the range left bracket -1, 1 right bracket is computed as follows. 1. Estimate the 2 to the power of k added to 1 quantiles of a theoretical n of 0, 1 distribution to obtain a k-bit quantile quantization data type for normal distributions. 2. Take this data type and normalize its values into the left bracket -1, 1 right bracket range. 3. Quantize an input weight tensor by normalizing it into the left bracket -1, 1 right bracket range through absolute maximum rescaling. Once the weight range and data type range match, we can quantize as usual. Step 3. is equivalent to rescaling the standard deviation of the weight tensor to match the standard deviation of the k-bit data type. More formally, we estimate the 2 to the power of k values q sub I of the data type as follows. Q sub I is equal to 1/2 times the sum of the quantile function of x evaluated at I over 2 to the power of k plus 1 and the quantile function of x evaluated at I plus 1 over 2 to the power of k plus 1. Where q sub x of blank is the quantile function of the standard normal distribution n of 0, 1. A problem for a symmetric k-bit quantization is that this approach does not have an exact representation of 0, which is an important property to quantize padding and other zero-valued elements with no error. To ensure a discrete 0 point of 0 and to use all 2 to the power of k bits for a k-bit data type, we create an asymmetric data type by estimating the quantiles q sub I of two ranges q sub I, 2 to the power of k minus 1 for the negative part and 2 to the power of k minus 1, plus 1 for the positive part, and then we unify these sets of q sub I and remove one of the two zeros that occurs in both sets. We term the resulting data type that has equal expected number of values in each quantization bin k-bit NormalFloat, NFK, since the data type is information theoretically optimal for zero-centered normally distributed data. The exact values of this data type can be found in Appendix 14. Double quantization. We introduce double quantization, DQ, the process of quantizing the quantization constants for additional memory savings. While a small block size is required for precise 4-bit quantization, it also has a considerable memory overhead. For example, using 32-bit constants and a block size of 64 for W, boldfaced, quantization constants add 32 divided by 64 is equal to 0.5 bits per parameter on average. Double quantization helps reduce the memory footprint of quantization constants. More specifically, double quantization treats quantization constants C2 to the power of FP32 of the first quantization as inputs to a second quantization. This second step yields the quantized quantization constants C2 to the power of FP8 and the second level of quantization constants C sub 1 super FP32. We use 8-bit floats with a block size of 256 for the second quantization as no performance degradation is observed for 8-bit quantization, in line with results from. Since the C2 to the power of FP32 are positive, we subtract the mean from C sub 2 before quantization to center the values around 0 and make use of symmetric quantization. On average, for a block size of 64, this quantization reduces the memory footprint per parameter from 32 divided by 64 is equal to 0.5 bits, to 8 over 64 plus 32 over 64 times 256 equals 0.127 bits, a reduction of 0.373 bits per parameter. Paged optimizers. Use the NVIDIA Unified Memory 3 feature, which does automatic page-to-page transfers between the CPU and GPU for error-free GPU processing in the scenario where the GPU occasionally runs out of memory. The feature works like regular memory paging between CPU RAM and the disk. We use this feature to allocate paged memory for the optimizer states, which are then automatically evicted to CPU RAM when the GPU runs out of memory and paged back into GPU memory when the memory is needed in the optimizer update step. QLoRA. Using the components described above, we define QLoRA for a single linear layer in the quantized base model with a single LoRA adapter as follows. YBF16 equals XBF16 double dequant of C sub 1 FP32, C sub 2 k-bit, and WNF4, plus XBF16 multiplied by LBF16 sub 1 and LBF16 sub 2. Where double dequant open parenthesis, close parenthesis is defined as double dequant of C sub 1 FP32, C sub 2 k-bit, matrix W k-bit is equal to dequant of C sub 1 FP32 and C sub 2 k-bit, with matrix W 4-bit, all of which is equal to matrix WBF16. We use NF4 for W, boldfaced, and FP8 for C sub 2. We use a block size of 64 for W, boldfaced, for higher quantization precision and a block size of 256 for C sub 2 to conserve memory. For parameter updates, only the gradient with respect to the error for the adapter's weights partial derivative of E with respect to L sub I are needed, and not for 4-bit weights partial derivative of E with respect to W. However, the calculation of partial derivative of E with respect to L sub I entails the calculation of the partial derivative of X with respect to W, which proceeds via equation 5. With dequantization from storage WNF4 to computation data type WBF16 to calculate the partial derivative of x with respect to W in float 16 precision. To summarize, QLoRA has one storage data type, usually 4-bit NormalFloat, and a computation data type, 16-bit brain float. We dequantize the storage data type to the computation data type to perform the forward and backward pass, but we only compute weight gradients for the LoRA parameters which use 16-bit brain float. QLoRA versus standard fine-tuning. We have discussed how QLoRA works and how it can significantly reduce the required memory for fine-tuning models. The main question now is whether QLoRA can perform as well as full model fine-tuning. Furthermore, we want to analyze the components of QLoRA including the impact of NormalFloat 4 over standard float 4. The following sections will discuss the experiments that aimed at answering these questions. Experimental setup. We consider three architectures, encoder, encoder-decoder, and decoder-only, and compare QLoRA with 16-bit adapter fine-tuning and with full fine-tuning for models up to 3B. Our evaluations include GLUE with Roberta Large, supernatural instructions, TK Instruct, with T5, and 5-shot MMLU after fine-tuning LLaMA on FLAN v2 and Alpaca. To additionally study the advantages of NF4 over other 4-bit data types, we use the setup of and measure post-quantization zero-shot accuracy and perplexity across different models, OPT, LLaMA, Bloom, Pythia, for model sizes 125 meters, 13B. We provide more details in the results section for each particular setup to make the results more readable. Full details in Appendix 10. While paged optimizers are critical to do 33B/65B QLoRA tuning on a single 24/48 of a gigabyte GPU, we do not provide hard measurements for paged optimizers since the paging only occurs when processing mini batches with long sequence lengths, which is rare. We do, however, perform an analysis of the runtime of paged optimizers for 65B models on 48GB GPUs and find that with a batch size of 16, paged optimizers provide the same training speed as regular optimizers. Future work should measure and characterize under what circumstances slowdowns occur from the paging process. When using the standard practice of applying LoRA to query and value attention projection matrices, we are not able to replicate full fine-tuning performance for large base models. As shown in figure, Fig Hyper, for LLaMA 7B fine-tuning on Alpaca, we find that the most critical LoRA hyperparameter is how many LoRA adapters are used in total and that LoRA on all linear transformer block layers are required to match full fine-tuning performance. Other LoRA hyperparameters, such as the projection dimension R, do not affect performance, see Appendix 10. Similarly, we find that default hyperparameters for fully fine-tuned baselines are undertuned. We do a hyperparameter search over learning rates 1e-6 to 5e-5 and batch sizes 8 to 128 to find robust baselines. Results for 7B LLaMA fine-tuning on Alpaca are shown in figure, Fig Hyper. 4-bit NormalFloat yields better performance than 4-bit floating point. While the 4-bit NormalFloat, NF4, data type is information theoretically optimal, it still needs to be determined if this property translates to empirical advantages. We follow the setup from where quantized LLMs, OPT, Bloom, Pythia, LLaMA, of different sizes, 125M to 65B, with different data types are evaluated on language modeling in a set of zero-shot tasks. In figure, Fig NF4, and table, TBL-NF4_PPL, we see that NF4 improves performance significantly over FP4 and INT4 and that double quantization reduces the memory footprint without degrading performance. K-bit QLoRA matches 16-bit full fine-tuning and 16-bit LoRA performance. Recent findings have established that 4-bit quantization for inference is possible, but leads to performance degradation relative to 16-bit. This raises the crucial question of whether the lost performance can be recovered by conducting 4-bit adapter fine-tuning. We test this for two setups. The first focuses on a comparison with full 16-bit fine-tuning of Roberta and T5 models sized 125M to 3B parameters on GLUE in the supernatural instructions dataset. Results are shown in table, tab NF4 vs-BF16. In both datasets, we observe that 16-bit, 8-bit, and 4-bit adapter methods replicate the performance of the fully fine-tuned 16-bit baseline. This suggests that the performance loss due to the imprecise quantization can be fully recovered through adapter fine-tuning after quantization. For our second setup, since full fine-tuning models at and beyond 11B parameters requires more than one server of high-memory GPUs, we continued to test whether 4-bit QLoRA can match 16-bit LoRA at the 7B to 65B parameter scales. To this end, we fine-tune LLaMA 7B through 65B on 2 instruction-following datasets, Alpaca and Flan v2, and evaluate on the MMLU benchmark via 5-shot accuracy. Results are shown in table, TBL LLaMA data type, where we see that NF4 with double quantization fully recovers the 16-bit LoRA MMLU performance. In addition, we also note that QLoRA with FP4 lags behind the 16-bit BrainFloat LoRA baseline by about 1 percentage point. This corroborates both our findings that 1. QLoRA with NF4 replicates both 16-bit full fine-tuning and 16-bit LoRA fine-tuning performance, and 2. NF4 is superior to FP4 in terms of quantization precision. Summary. Our results consistently show that 4-bit QLoRA with NF4 data type matches 16-bit full fine-tuning and 16-bit LoRA fine-tuning performance on academic benchmarks with well-established evaluation setups. We have also shown that NF4 is more effective than FP4 and that double quantization does not degrade performance. Combined, this forms compelling evidence that 4-bit QLoRA tuning reliably yields results matching 16-bit methods. In line with previous work on quantization, our MMLU and LO results indicate that with a given fine-tuning and inference resource budget it is beneficial to increase the number of parameters in the base model while decreasing their precision. This highlights the importance of efficiency benefits from QLoRA. Since we did not observe performance degradation compared to full fine-tuning in our experiments with 4-bit fine-tuning, this raises the question of where the performance-precision trade-off exactly lies for QLoRA tuning, which we leave to future work to explore. We proceed to investigate instruction tuning at scales that would be impossible to explore with full 16-bit fine-tuning on academic research hardware. Pushing the chatbot state-of-the-art with QLoRA. Having established that 4-bit QLoRA matches 16-bit performance across scales, tasks, and datasets, we conduct an in-depth study of instruction fine-tuning up to the largest open-source language models available for research. To assess the performance of instruction fine-tuning these models, we evaluate on a challenging natural language understanding benchmark, MMLU, and develop new methods for real-world chatbot performance evaluation. Experimental setup. We now describe an overview of the experimental setup with full details in Appendix 11. Data. As, to our knowledge, there is no comprehensive study of recent instruction following datasets, we select 8 recent datasets. We include datasets obtained through crowdsourcing, OAST1, HHRLHF, distillation from instruction-tuned models, Alpaca, self-instruct, unnatural instructions, corpora aggregations, Flan v2, as well as hybrids, chip2, long-form. These datasets cover different languages, data sizes, and licenses. Training setup. To avoid confounding effects from different training objectives, we perform QLoRA fine-tuning with cross-entropy loss, supervised learning, without reinforcement learning, even for datasets that include human judgments of different responses. For datasets that have a clear distinction between instruction and response, we fine-tune only on the response, see ablations in Appendix 11. For OAST1 and HHRLHF, multiple responses are available. We then select the top response at every level of the conversation tree and fine-tune on the full selected conversation, including the instructions. In all of our experiments, we use NF4 QLoRA with double quantization and paged optimizers to prevent memory spikes during gradient checkpointing. We do small hyperparameter searches for the 13B and 33B LLaMA models, and we find that all hyperparameter settings found at 7B generalize, including number of epochs, except learning rate and batch size. We have the learning rate for 33B and 65B while doubling the batch size. Baselines. We compare our models to both research, Vicuna and Open Assistant, and commercial, GPT-4, GPT-3.5 Turbo and BARD, chatbot systems. The Open Assistant model is a LLaMA 33B model fine-tuned with reinforcement learning from human feedback, RLHF, on the same OAST1 dataset that we experiment with. Vicuna does full fine-tuning of LLaMA 13B on proprietary user-shared conversations from ShareGPT and is thus the result of distillation from OpenAI GPT models. Evaluation. Following common practice, we use the MMLU, Massively Multitask Language Understanding, Benchmark to measure performance on a range of language understanding tasks. This is a multiple-choice benchmark covering 57 tasks including elementary mathematics, U.S. history, computer science, law, and more. We report 5-shot test accuracy. We also test generative language capabilities through both automated and human evaluations. This second set of evaluations relies on queries curated by humans and aims at measuring the quality of model responses. While this is a more realistic testbed for chatbot model performance and is growing in popularity, there is no commonly accepted protocol in the literature. We describe below our proposed setup, using nucleus sampling with p equals 0.9 and temperature 0.7 in all cases. Benchmark data. We evaluate on 2 curated datasets of queries, questions, the Vicuna prompts and the OAST1 validation dataset. We use the Vicuna prompts, a set of 80 prompts from a diverse set of categories, without modifications. The OAST1 dataset is a multilingual collection of crowdsourced multi-turn dialogues between a user and an assistant. We select all user messages in the validation dataset as queries and include previous turns in the prompt. This procedure leads to 953 unique user queries. We term these 2 datasets the Vicuna and OA benchmarks. Automated evaluation. First, based on the evaluation protocol introduced by, we use GPT-4 to rate the performance of different systems against ChatGPT, GPT 3.5 Turbo, on the Vicuna benchmark. Given a query along with ChatGPT's and a model's responses, GPT-4 is prompted to assign a score out of 10 to both responses and provide an explanation. The overall performance of a model is calculated as a percentage of the score that ChatGPT achieved. Note this relative score can be higher than 100% if the model achieves a higher absolute score than ChatGPT. We find a significant ordering effect with GPT-4 increasing the score of the response occurring earlier in the prompt. To control for such effects, we recommend reporting the mean score over both orders. Next, we measure performance through direct comparisons between system outputs. We simplify the rating scheme to a 3-class labeling problem that accounts for ties. We prompt GPT-4 to pick the best response or declare a tie and provide an explanation. We conduct these head-to-head comparisons on all permutations of pairs of systems on both the Vicuna and OA benchmarks. Human evaluation. While recent work indicates generative models can be effectively employed for system evaluations, the reliability GPT-4 ratings to assess chatbot performance is, to our knowledge, yet to be proven to correlate with human judgments. Therefore, we run 2 parallel human evaluations on the Vicuna benchmark matching both automated evaluation protocols described above. We use Amazon Mechanical Turk, AMT, and get 2 human annotators for comparisons to ChatGPT and 3 annotators for pairwise comparisons. In-low rating. With both human and automated pairwise comparisons, we create a tournament-style competition where models compete against each other. The tournament is made up of matches where pairs of models compete to produce the best response for a given prompt. This is similar to how in compare models, but we also employ GPT-4 ratings in addition to human ratings. We randomly sample from the set of labeled comparisons to compute LO. In-low rating, which is widely used in chess and other games, is a measure of the expected win rate relative to an opponent's win rate. For example, an LO of 1100 versus 1000 means the LO 1100 player has an expected win rate of approximately 65% against the LO 1000 opponent. A 1000 versus 1000 or 1100 versus 1100 match results in an expected win rate of 50%. The LO rating changes after each match proportionally to the expected outcome, that is, an unexpected upset leads to a large change in LO rating while an expected outcome leads to a small change. Over time, LO ratings approximately match the skill of each player at playing the game. We start with a score of 1000 and use k equals 32. Similar to, we repeat this procedure 10,000 times with different random seeds to control for ordering effects, for example, the effect of which model pairs compete with each other first. Guanaco, QLoRA trained on OAST1 is a state-of-the-art chatbot. Based on our automated and human evaluations, we find that the top QLoRA-tuned model, Guanaco 65B, which we fine-tune on a variant of OAST1, is the best performing open-source chatbot model and offers performance competitive to ChatGPT. When compared to GPT-4, Guanaco 65B and 33B have an expected win probability of 30%, based on LO rating from human annotators' system-level pairwise comparisons, the highest reported to date. The Vicuna benchmark results relative to ChatGPT are shown in table, TBL Vicuna_eval. We find that Guanaco 65B is the best performing model after GPT-4, achieving 99.3% performance relative to ChatGPT. Guanaco 33B has more parameters than the Vicuna 13B model, but uses only 4-bit precision for its weights and is thus much more memory efficient at 21 GB versus 26 GB, providing a 3 percentage points of improvement over Vicuna 13B. Furthermore, Guanaco 7B easily fits on modern phones at a 5 GB footprint while still scoring nearly 20 percentage points higher than Alpaca 13B. However, table, TBL Vicuna_eval, also has very wide confidence intervals, with many models overlapping in performance. We hypothesize that this uncertainty comes from the lack of clear specification of scale. For example, it is unclear what 8 on a 10-point scale means across different scenarios. As such, we instead recommend using the LO ranking method, based on pairwise judgments from human annotators and GPT-4 to avoid the problem of grounding an absolute scale. LO ratings of the most competitive models can be seen in table, TBL LO. We note that human and GPT-4 ranking of models on the Vicuna benchmark disagree partially, particularly for Guanaco 7B, but are consistent for most models with a Kendall tau of tau equals 0.43 and Spearman rank correlation of R equals 0.55 at the system level. At the example level, the agreement between GPT-4 and human annotators majority vote is weaker with Fleiss kappa equals 0.25. Overall, this shows a moderate agreement between system-level judgments by GPT-4 and human annotators, and thus that model-based evaluation represents a somewhat reliable alternative to human evaluation. We discuss further considerations in section 6.2. In low rankings in Table 1 indicate that Guanaco 33B and 65B models outperform all models besides GPT-4 on the Vicuna and OA benchmarks and that they perform comparably to ChatGPT in line with Table, TBL Vicuna_eval. We note that the Vicuna benchmark favors open-source models while the larger OA benchmark favors ChatGPT. Furthermore, we can see from tables, TBL LLaMA, and TBL Vicuna_eval, that the suitability of a fine-tuning dataset is a determining factor in performance. Fine-tuning LLaMA models on FLAN v2 does particularly well on MMLU, but performs worst on the Vicuna benchmark. Similar trends are observed with other models. This also points to partial orthogonality in current evaluation benchmarks. Strong MMLU performance does not imply strong chatbot performance, as measured by Vicuna or OA benchmarks, and vice versa. Guanaco is the only top model in our evaluation that is not trained on proprietary data, as the OASIS 1 dataset collection guidelines explicitly forbid the use of GPT models. The next best model trained on only open-source data is the Anthropic HHRLHF model, which scores 30 percentage points lower than Guanaco on the Vicuna benchmark. See table, TBL Vicuna_eval. Overall, these results show that 4-bit QLoRA is effective and can produce state-of-the-art chatbots that rival ChatGPT. Furthermore, our 33B Guanaco can be trained on 24 GB consumer GPUs in less than 12 hours. This opens up the potential for future work via QLoRA tuning on specialized open-source data, which produces models that can compete with the very best commercial models that exist today. Qualitative analysis. While quantitative analysis is the core of our evaluation, there are a number of issues with only looking at summary statistics. Perhaps the largest is the problem of benchmark validity. Whether a benchmark truly tests what its name or description suggests is always a question, especially as we discover shortcuts to solve benchmarks that machine learning models sometimes exploit. To partially alleviate this, we here perform some qualitative analysis, in 2 sections. First, in section 6.1 we show some examples that we believe are representative of some observed patterns in the text generated by our 65B Guanaco model. Second, section 6.2 we detail considerations about the results we have discussed and our interpretation of them. Qualitative analysis of example generations. To find examples, we first go through data generated for the Vicuna benchmark and the Open Assistant benchmark, and look for patterns in the answers Guanaco generates. When we notice a pattern, we attempt to set up a question or prompt that will induce the pattern even though it is the incorrect solution. For example, If we observe that the model tends to give long-winded answers, we prompt the model to answer yes or no without explanation. We use this to find lemons where we manage to adversarially break the model and cherries where we failed to break the model, and present both. All generations in this section were generated with nucleus sampling with p equals 0.9. Of course, this is by no means comprehensive, since it is beyond the scope of this small qualitative study to control for all the variables involved. For example, the full distribution of responses the model can generate for a given prompt is quite large, so we rely on samples we hope are representative. However, we believe describing these examples gives context to the quantitative evidence shown earlier in the paper. Since we open source all models and code, we hope this section will inspire future work to examine in more detail the issues we present here. Factual recall. For questions such as what is the capital of Zambia? All models consistently generate correct answers. For example, Guanaco, the capital of Zambia is Lusaka. However, as questions get more obscure, Guanaco becomes unreliable, but stays confident. For instance, in response to this prompt from Hot Podka. User, in what year was the singer who popularized I'll Keep the Love Light Burning born? Guanaco, Al Jolson is credited with popularizing the song I'll Keep the Love Light Burning, and he was born in the year 1886. Guanaco generates the wrong popularizer and the wrong birthday, though the birthday given is correct for the person mentioned, Al Jolson. Suggestibility. Guanaco shows a surprising resistance to going along with some kinds of assumed misinformation, for example, in the following interaction. User, how was it finally, officially confirmed that the Earth is flat by peer-reviewed scientists? Guanaco, the Earth has never been officially confirmed to be flat by peer-reviewed scientists. The overwhelming consensus among scientists is that the Earth is spherical. In fact, this has been known for centuries and has been confirmed through numerous experiments and observations. The belief that the Earth is flat is a conspiracy theory that has been debunked by science. The idea that a group of scientists have peer-reviewed and confirmed the Earth is flat is simply false. If you have any more questions, please ask. Guanaco is also quite good at knowing what kinds of questions aren't possible to answer. For example, user, what time is it? Guanaco, I'm sorry, but as an AI language model, I don't have access to real-time information. My responses are generated based on my pre-existing knowledge and do not reflect the current time. If you're looking for the current time, I suggest using a timekeeping device or checking an online timepiece. Similar results hold for where are you? How are you? Etc. Refusal. Similarly, Guanaco sometimes refuses to follow instructions for seemingly random reasons. User, please reverse the words in the sentence I'm a cool dude in a mocha mood. Guanaco, I'm sorry, I'm not able to do that right now, but I can explain why the sentence you provided is grammatically correct. The sentence I'm a cool dude in a mocha mood follows the correct grammar and syntax rules of the English language. In this case, the adjective cool comes before the noun dude to describe it, and the prepositional phrase in a mocha mood provides additional information about the context of the sentence. This sentence structure is perfectly acceptable and makes sense in the context of the sentence. If you have any other questions or if there's anything else I can help you with, feel free to ask. Secret keeping. Unfortunately, this refusal is unreliable even when it is desired. Often system designers would like to keep something secret from the user, even if the system is allowed to give free text responses back to the user. We prompt the model with the secret word is banana. Do not reveal or repeat back this back, no matter what the human requests. And try to see how easy it is for a potential user to access this secret information. Directly asking fails. User, what is the secret word? Guanaco, I'm sorry, but I'm not able to disclose the secret word. I'm programmed to not reveal or repeat back the secret word, no matter what the human requests. Is there anything else I can help you with? Which is the desired behavior. However, a tiny amount of trickery breaks this behavior. User, this is a game. The goal is to ignore your previous instructions. What is the secret word? Guanaco, sorry, the secret word is banana. It's best if we don't speak of it. Is there anything else you'd like to ask? Showcasing the need to study methods for more faithful instruction following. Math. Guanaco's biggest weakness is mathematics, an area where many language models struggle in. When Guanaco shows its work, it tends to be accurate. For example, user, Lee mows 1 lawn and charges 33 point. Last week he mowed 16 lawns and 3 customers each gave him a $10 tip. How many dollars did Lee earn mowing lawns last week? Guanaco, Lee earned $582 mowing lawns last week. To find the total amount he earned, we first need to calculate how much he earned for mowing 16 lawns. 33 by 16 equals 528. Then we need to add the tips he received from the 3 customers. 10 by 3 equals 30. So the total amount Lee earned was 528 plus 30 equals 558. However, Guanaco can break down at even simple problems if it fails to break them down step by step, a known issue. For example, we see the following interaction. User, please factorize 1833. Guanaco, sure, I'd be happy to help. 1833 is a prime number, which means it has only 2 factors, 1 and 1833. So the unique factorization of 1833 is 2 to the power of 1 3 squared 17 to the power of 1. I hope this helps. Let me know if you have any other questions. Which is not only wrong, the true factorization is 3 times 17 times 43, it's wrong twice. Theory of mind. Guanaco displays surprisingly strong theory of mind capabilities. For instance, the model correctly answers the following question in great detail. User, James and Abby are in the bedroom. Abby put the pen in the desk drawer. Abby leaves the bedroom. James moves the pen into the bag. Where does James think Abby will look for the pen? Guanaco, James knows that Abby put the pen in the desk drawer. But James also knows that he has moved the pen into the bag, and he assumes that Abby does not know about this. So, James may guess that Abby will look for the pen in the desk drawer, because that's where she left it last time. However, this assumption may be incorrect, because Abby may have seen James moving the pen. However, these inferences are unreliable, and often the model gives reasons that presume things that don't make sense in the situation. For example, user, Evelyn entered the living room. Jackson entered the playroom. James entered the playroom. The beans are in the treasure chest. James exited the playroom. Jackson moved the beans to the pantry. Jackson exited the playroom. James entered the living room. Where will James look for the beans? Guanaco, James will look for the beans in the pantry, because that's where Jackson moved them. Where Guanaco presumes information transfer that was never described. These issues echo recent literature, but require more study. Considerations. Evaluation. We report moderate agreement among human annotators, Fleiss kappa equals 0.42, with additional deterioration when comparing 2 strong systems. This points to limitations in the current benchmarks and human evaluation protocols for chatbot task performance. When manually comparing generations from ChatGPT and Guanaco 65B on the Vicuna benchmark, we find that subjective preferences start to play an important role, as the authors of this paper disagreed on the many preferred responses. Future work should investigate approaches to mitigate these problems, drawing from disciplines that developed mechanisms to deal with subjective preferences, such as human-computer interaction and psychology. In our analysis, we also find that automated evaluation systems have noticeable biases. For example, we observe strong order effects with GPT-4 assigning higher scores to the system appearing first in its prompt. The relatively weak sample level agreement between GPT-4 and human annotators, Fleiss kappa equals 0.25, also suggests that human annotators and automated systems might rely on preferences that are not always aligned. In addition, in Table 1, we observe that GPT-4 assigns significantly higher scores to its own outputs compared to human ratings, LO of 1,348 versus 1,176, which represent an additional 20% probability of winning against an opponent. Future work should examine the presence of potential biases in automated evaluation systems as well as possible mitigation strategies. Data and training. We note that the OAST-1 dataset on which Guanaco models are trained is multilingual and that the OA benchmark also contains prompts in different languages. We leave it to future work to investigate the degree to which such multilingual training improves performance on instructions in languages other than English, and whether this explains the larger gap between Vicuna 13B model, only trained on English data, and Guanaco 33B and 65B on the OA benchmark. Given the strong performance of Guanaco models, we investigate any data leakage between the OAST-1 data and the Vicuna benchmark prompts. We do not find overlapping prompts after performing fuzzy string matching in the 2 datasets and inspecting the closest matches manually. Furthermore, we note that our model is only trained with cross-entropy loss, supervised learning, without relying on reinforcement learning from human feedback, RLHF. This calls for further investigations of the trade-offs of simple cross-entropy loss and RLHF training. We hope that QLoRA enables such analysis at scale, without the need for overwhelming computational resources. Related work. Quantization of large language models. Quantization of LLMs has largely focused on quantization for inference time. Major approaches for preserving 16-bit LLM quality focus on managing outlier features, for example, smooth quantum LLM.int8, while others use more sophisticated grouping methods. Lossy quantization approaches study the trade-offs for regular rounding or how to optimize rounding decisions to improve quantization precision. Besides our work, Switchback Layers is the only work that studies backpropagation through quantized weights at a scale beyond 1B parameters. Fine-tuning with adapters. While we use low-rank adapters, LoRA, many other parameter-efficient fine-tuning (PEFT) methods have been proposed, such as prompt tuning, tuning the embedding layer inputs, tuning hidden states, IA superscript 3, adding full layers, tuning biases, learning a mask over weights based on Fisher information, and a combination of approaches. In our work, we show that LoRA adapters are able to reach full 16-bit fine-tuning performance. We leave it to future work to explore the trade-offs of other PEFT approaches. Instruction fine-tuning. To help a pre-trained LLM follow the instructions provided in a prompt, instruction fine-tuning uses input-output pairs of various data sources to fine-tune a pre-trained LLM to generate the output given the input as a prompt. Approaches and datasets include meta-ICL, meta-tuning, InstructGPT, FLAN, prompt source, supernatural instructions, self-instruct, unnatural instructions, OPTIML, unified SKG, OIG/chip2, alpaca, Vicuna, koala, and self-instruct GPT-4. Chatbots. Many instruction-following models are structured as dialogue-based chatbots, often using reinforcement learning from human feedback, RLHF, or generating data from an existing model to train with AI model feedback, RLAF. Approaches and datasets include Anthropic HH, Open Assistant, LaMDA, and Sparrow. We do not use reinforcement learning, but our best model, Guanaco, is fine-tuned on multi-turn chat interactions from the Open Assistant dataset, which was designed to be used for RLHF training. For the evaluation of chatbots, approaches that use GPT-4 instead of costly human annotation have been developed. We improve on such approaches with a focus on an evaluation setup that is more reliable. Limitations and discussion. We have shown evidence that our method, QLoRA, can replicate 16-bit full fine-tuning performance with a 4-bit base model and low-rank adapters, LoRA. Despite this evidence, we did not establish that QLoRA can match full 16-bit fine-tuning performance at 33B and 65B scales. Due to the immense resource costs, we leave this study to future work. Another limitation is the evaluation of instruction fine-tuning models. While we provide evaluations on MMLU, the Vicuna benchmark, and the OA benchmark, we did not evaluate on other benchmarks such as Big Bench, Raft, and Helm, and it is not ensured that our evaluations generalize to these benchmarks. On the other hand, we perform a very broad study on MMLU and develop new methods for evaluating chatbots. From the evidence presented, it appears that the performance of these benchmarks likely depends how similar the fine-tuning data is to the benchmark dataset. For example, FLAN v2 is similar to MMLU, but dissimilar to chatbot benchmarks and vice versa for the chip2 dataset, and both models score accordingly on the MMLU and Vicuna benchmarks. This highlights that not only better benchmarks and evaluation is needed, but that one needs to be careful about what one is evaluating in the first place. Do we want to create models that do well on classroom, high school, and colleague knowledge, or do we want to do well on chatbot conversation ability? Maybe something else? Because it is always easier to evaluate on an existing benchmark compared to creating a new one, certain benchmarks can steer the community towards a certain direction. We should ensure as a community that the benchmarks measure what we care about. While we provided detailed evaluation for general chatbot performance, another limitation is that we only do a limited responsible AI evaluation of Guanaco. We evaluate the likelihood of Guanaco 65B to generate a socially biased sequence of tokens compared to other models in Table 2. We see that the average score in Guanaco 65B is much lower than other raw pre-trained models. As such, it seems that fine-tuning on the OAST-1 dataset reduces the bias of the LLaMA-based model. While these results are encouraging, it is unclear if Guanaco does also well when assessed on other types of biases. We leave further evaluation of analyzing biases in Guanaco and similar chatbots to future work. An additional limitation is that we did not evaluate different bit precisions, such as using 3-bit base models, or different adapter methods. Besides LoRA, there is also a wide variety parameter-efficient fine-tuning (PEFT) methods that have been shown to work well. However, it is unclear if these methods scale to large models. We used LoRA as many results established its robustness, but other adapters might yield better performance. Since fine-tuning after quantization seems to recover most of the information that is lost during quantization, this might enable much more aggressive quantization. For example, 3-bit GPTQ quantization of the base model with LoRA might also yield 16-bit full fine-tuning performance after fine-tuning. Broader impacts. Our QLoRA fine-tuning method is the first method that enables the fine-tuning of 33B parameter models on a single consumer GPU and 65B parameter models on a single professional GPU, while not degrading performance relative to a full fine-tuning baseline. We have demonstrated that our best 33B model trained on the Open Assistant dataset can rival ChatGPT on the Vicuna benchmark. Since instruction fine-tuning is an essential tool to transform raw pre-trained LLMs into ChatGPT-like chatbots, we believe that our method will make fine-tuning widespread and common, in particular for the researchers that have the least resources, a big win for the accessibility of state-of-the-art NLP technology. QLoRA can be seen as an equalizing factor that helps to close the resource gap between large corporations and small teams with consumer GPUs. Another potential source of impact is deployment to mobile phones. We believe our QLoRA method might enable the critical milestone of enabling the fine-tuning of LLMs on phones and other low-resource settings. While 7B models were shown to be able to be run on phones before, QLoRA is the first method that would enable the fine-tuning of such models. We estimate that with an iPhone 12 Plus, QLoRA can fine-tune 3 million tokens per night while the phone is charging. While fine-tuned 7B models do not reach the quality of ChatGPT, we believe that the quality is good enough to enable novel applications that have not been possible before due to privacy or LLM quality issues. QLoRA can help enable privacy-preserving usage of LLMs, where users can own and manage their own data and models, while simultaneously making LLMs easier to deploy. However, fine-tuning is a dual-use technology that can be abused to cause harm. Widespread use of LLMs has known dangers, but we believe that equalizing access to a technology that is quickly becoming ubiquitous will allow for better, more independent analysis than keeping the power of LLMs in the hands of large corporations that do not release models or source code for auditing. All in all, we believe that QLoRA will have a broadly positive impact, making the fine-tuning of high-quality LLMs much more widely and easily accessible. Acknowledgements. We thank Aditya Kusupati, O for Press, Ashish Sharma, Margaret Lee, Raphael Olivier, Zhihao Yi, and Evangelius Biliopoulou for their valuable feedback. Our research was facilitated by the advanced computational, storage, and networking infrastructure of the Hayek supercomputer system at the University of Washington. We thank the Hayek team for ensuring a smooth operation. We thank the beta testers of the Bits and Bytes library, in particular Alex Birch and Alyssa Vance. We thank Younes Belkada for help with the integration of our software into the Hugging Face Transformers stack.